So thank you for inviting me to this workshop. So don't hesitate to interrupt if you're completely lost. I'm going to sort of describe briefly at the beginning the overall idea about Bayesian asymptotics in high-dimensional models. And then I'll concentrate on some recent results we've obtained to get measures of asymptoticity in high-dimensional models. So general setup to begin with, and then Sorry. So just to define notations, you've got data, xn. So I index it by n because n is going to go to infinity at some stage. Whose distribution depends on some parameter p theta, and typically theta will be infinite dimensional. And so we're Bayesian, so we put a prior on theta. And so pi is a prior, and then once you have that, then you have xn given theta follows p theta, theta follows pi, and so you've got the joint distribution on xn and theta. And if you invert the probability, then you get what's called the posterior distribution, which is the conditional distribution of the parameter given the data. And in dominated model, it's proportional to what's the likelihood. So that's the density of this guy times the prior. And m of xn is the marginal likelihood. And so that's sort of the setup for notations. And all the Bayesian inference is based on the posterior distribution. So that's sort of the object with which you're going to work. And so the aim of the game is to understand how it's going to behave in high-dimensional models. So high-dimensional starts by d equals 1. So just to illustrate the kind of things I'm interested about, so you have data ID Poisson theta, and theta is in R+. And you put a gamma prior on theta because then you have easy computation. So the posterior is also gamma in this case. And I have plotted a plot here. So when you go down the rows, n increases from 10 to something, 1,000, 100, no, 1 to 100. And then for different columns, you have different values of the parameters. So the red is the prior, the black is the posterior. And sort of what you see is when n is small, the prior is quite influential. So there is a difference between the behavior of the posterior from the left to the right. And so the prior did make a difference. When n increases, the prior doesn't make a difference anymore. So that's the first sort of comment that you can make. The second comment is that as n increases, the posterior becomes more and more concentrated. And third comment is as n increases, the posterior looks more and more like a Gaussian. And that's the kind of things that are typical in parametric models. Well, I've said that. So yeah, that's typical in parametric models, irregular parametric models. And the question is, how can you extend these kind of statements in high dimensions? And why would you do that? So what I mean by high dimensions, I'm meaning non-parametrics or semi-parametrics. And so just examples of non-parametric models. So you have a regression function, a regression model. So f of x, in this case, f is the object of interest. And then the parameter space is L2. If you do density estimation, then the object is a density. And then the parameter space is a space of densities on whatever you're living in. But you can do all sorts of things, of course, classification, spectral density estimation, intensity function for point process, conditional density. I mean, you can imagine it, whatever you want. Huh? So that's sort of the setup. And so now the parameter space is infinite dimensional. So we do not have d equals 1 anymore. We have something more than that. So the kind of building blocks, typical building blocks when you do Bayesian non-parametrics are Gaussian processes and Dirichlet process. So just to illustrate, I'm going to talk about Gaussian processes just to show, to give you an idea on really the kind of different behavior you get if you put a certain type of prior. So if you take a Gaussian process prior, what's a Gaussian process prior? It means that you're modeling your function here, f, as a Gaussian process. In other words, for any finite evaluations of the function, so you look at f of x1 to f of xq. And so this is a vector in this case. For any x1 up to xq, this big vector is a Gaussian vector with mean 0 if it's a centered Gaussian process, and covariance matrix given by some kernel k, which is sort of the same kernel that was mentioned before for the RKHS story. So k is a covariance matrix, a covariance kernel evaluated at xi and xj. And k is very important. So it entirely drives the smoothness of the curve that you're going to draw if you draw from this Gaussian process. Just two illustrations to show you how important that is. This is a Brownian motion, so it's very rough. And this is an exponential, so the exponential kernel that was mentioned in the previous talk before. So this is very smooth. And so it has an impact on the kind of curves that you're drawing. If you draw from the Brownian motion, it's very rough. If you draw from the exponential kernel, it's very rough, very smooth. But that's not only this. The measures of uncertainty that are associated to each of these kernels are also extremely different. If you were to draw measures of uncertainty around there, they would be all over the place. Here, they will be really tight around that one. So it's much tighter for smooth kernels than for non-smooth kernels. So you do not only make an assumption on the kind of curves that you're making, but you also make a really strong assumption on the kind of measures of uncertainty that you're going to get at the end of the day. So that's understanding these kind of things is important. And in particular, the question that you're asking is that, so I have my prior, I make a certain decision on my prior. What's going to happen for the posterior? Is the data going to swamp this effect or not? Or what's going to remain asymptotically, and what kind of assumption does it sort of imply? Another type of priors that's sort of similar. Somehow you can look at the Gaussian process as something and you expand it on the basis. It's just exactly what was said in the talk before. So if now you can construct directly your prior on writing the basis expansion, and then you can either truncate at k randomly or not randomly, or you put k equal to infinity, and then you fix you take Gaussian k theta i's. So there is a random truncation story. I'm going to come back to it because this is what we've been working on. So k follows a prior pk, and then given k, so you consider only the first k coefficients in your expansion, then you choose a prior on the theta i's. For instance, Gaussian prior with variance tau I, but it can be really anything else. And you can have tau I equals to a constant or tau I decreasing if you want to shrink. But essentially, because you've put a prior on k, you're going to shrink anyway. The other version is to take the Gaussian process, essentially. So k equals infinity. And then you have these variances. And then depending on how fast the variance goes to infinity, you're going to have smoother or rougher paths. So if the variances go to zero, if the variances go to zero very fast, then it's a very smooth path. So like the double exponential. If the variance go to zero slowly, then it's a bit like the Brownian motion. It's very rough. So that's the one part of the story is to understand the impact of these hyperparameters. And then which are the hyperparameters that are really influential, and they are the ones that will not disappear asymptotically, essentially. How can we get a better adaptive behavior of that? And so you can sort of, and then also understand the measure of asymptoticity associated to these choices. So this, one way to try to understand these sort of statements is to look at asymptotics, because in the asymptotic world, things are simpler somehow. And so you make your life easier, and you see what's there and what's not there anymore. So looking at the first type of result that you can look is consistency. And there is quite a lot of work on consistency. You can refine the analysis by looking at concentration rates, and I'm going to describe what it means. And then you can try to be even more refined by trying to look at whether the posterior distribution looks more and more like a Gaussian, which is what we saw for the Poisson example. And that's called Bernstein von Mises. And in semi-parametric models, there is now some results on that. But this is asking quite a lot if you wanted to have that for the whole parameter. And so you can ask for slightly less and look at balls and look at the credible balls and see whether these credible balls also have frequentist confidence balls. And that's, when you're saying something like that, you can answer it by Bernstein von Mises, but you can answer it using less stringent conditions. And that's what I'm going to describe at the end of the talk. So first, the kind of more basic asymptotic result that you can ask, which is consistency or convergence rates. So consistency, what does it mean? It means that so you're going to be frequentist for this. So although you have a Bayesian modeling, you still assume that there is a true theta naught, and you want to see whether if the data were associated to this theta naught, so coming from theta naught, does the posterior distribution concentrate for each fixed neighborhood? Does the posterior concentrate on this fixed neighborhood, whatever the neighborhood I'm considering? So if you have that, then it means that you're consistent because the posterior puts all its mass around the truth. But the question that you can ask is that not only do I want to see whether it concentrates, but how fast is it going to shrink? And if you look at the rate at which the posterior concentrates, in other words, it corresponds to oops, what did I do? No. It corresponds to looking at shrinking neighborhoods. So epsilon this time it goes to 0. So you're looking at neighborhoods that are smaller and smaller around the truth. But still, the posterior probability of these neighborhoods goes to 1 as n goes to infinity. So it still captures most of the mass. And you want to find the epsilon n that goes to 0 as fast as possible such that you have these. So this is looking at posterior concentration rates. And really, you can look at them as looking at level sets of the posterior distribution, in other words, and trying to understand how fast they shrink towards the truth. And this depends on the distance d that you're considering for the balls, but it depends also typically on smoothness conditions or features of theta naught and on your prior. This is a well-known subject to some extent. So there is a huge literature now over the last 10 or 15 years on that, thanks to the work of Gosel and van der Waart. They were really like the beginners of the story. And all sorts of models have been considered, all sorts of priors have been considered, and all combinations of that have been considered. And in particular, what's appeared when you do that is that because Bayesians are great ways of considering hierarchical modeling, by putting a prior on these hyperparameters, you get adaptive estimation. In other words, you're learning the smoothness of the truth. You're learning these key features in the truth that makes that your rate is going to be whatever it's supposed to be, essentially by the data. And so that's a great story, essentially, because Bayesians are a natural way to be optimal, in some sense. But that's only concentration rates. Does it tell us something about the measures of uncertainty? If I consider a credible region, how is it true that it is also going to be a confidence region asymptotically? It's not quite clear. So what does it mean to look at credible? Oops, décidément. This is the other one. So what does it mean to look at credible regions? It means that I'm looking at a ball, for instance, or a region, C alpha, such that the posterior probability of belonging to C alpha is equal to 1 minus alpha. So that's a definition of a credible region. So the typical ones are HPD regions, or credible balls, or credible equal tail intervals if you are in looking at one-dimensional objects. And so if you have this, then if you do Fibini, it's with a simple Fibini argument, what you have is that on average, you also be a confidence region. What I mean by being a confidence region is mean that the frequentist probability under p theta that theta belongs to the region is equal to 1 minus alpha. So this is not true for all theta, but it's true on average with respect to the prior. Is it enough? In parametric model, you could imagine that it's almost enough because the prior is essentially like a continuous density on the RD. And so if it's true on average under the prior, it shouldn't be too bad for most theta. The problem is that the priors in high-dimensional objects are living in sub-varieties of much smaller dimension. It's a bit like as if they were living on points in a plane. They're really living on a sparse aspect of your model, but the closure of the space on which they live is the whole space. And so when it's true on average, it doesn't mean that it's true for a lot of theta. On the contrary, it doesn't really mean anything in terms of that. And so the question is, for which theta is it going to be true, these kind of statements? And that's the question we've been wondering. Can we say something about at least a subset of the parameter space for which we know that the coverage of these regions is not too bad? So does the posterior concentration rate helps there, or what does it tell us in terms of these credible regions? If you look, so I recall what I mean by posterior concentration rates. It means that I'm looking at balls around the truth of radius epsilon n such that the posterior probability of this ball goes to 1. If I'm looking at a credible ball for the same d, I'll be picking up some estimator, like the posterior mean, for instance. And then I'll be looking at a ball with radius q alpha, such that the posterior probability of this guy is equal to 1 minus alpha. In other words, q alpha of x is the posterior quantile of this object as a function of theta. Okay? And what happens is that if you do have these, if you define C alpha like that and you have posterior concentration rates, then the only information that you get from the posterior concentration rate is the fact that the size of your set is epsilon n, essentially. So the posterior concentration rates tell you something on the size of the set. It doesn't tell you anything on the coverage of the set, the frequentist coverage of the set. So you have to do something else to understand how it works. And that's much more refined. That's much more difficult to be able to say something like that. So just to go back to simple things and to make mathematical what I did show with the plots at the beginning of the talk, what happens in the parametric world? In the parametric world, if you have a regular model, you have this sort of famous Bernstein-Van-Mises theorem that says that asymptotically, the posterior distribution looks like a Gaussian with mean the MLE and variance the inverse of the Fisher information matrix. So asymptotically, you've got this Gaussian shape, but not only do you have a Gaussian shape, the mean of this posterior distribution is the MLE, and the asymptotic posterior variance is the same as the asymptotic frequencies variance of the MLE. And this duality, the fact that you have the same behavior in the frequencies and the Bayesian work, will induce the fact that credible regions will also be confidence regions. And that's the magic of it. But in the infinite dimensional case, is it true anymore? Or is it still true, I think? So how can we extend these results to high-dimensional models and to get these strong kind of statements? It's a very strong statement, and in high-dimensional models, you can expect it not to be true. But, or if it's true, then it's going to depend strongly on the choice of the prior. You could make it weaker by looking only at some parametric aspect or finite dimensional aspect of your prior, of your parameters. And that's looking at semi-parametric Bernstein-Van-Mises. And that's true in some cases. And you can give counterexample and the good examples. And there is a small literature on that now. But if you want to look at the whole parameter, you can try to get something weaker. And that's what I'm going to talk about, to look at a weaker statement than what I've just said. So just recalling the aim of the game here. So I'm looking at a credible ball around some posterior mean, say, for some distance d. So the posterior probability of this is equal to 1 minus alpha. And I want to understand the frequencies coverage of these kind of guys. I know that on average is good, but for which theta is it going to be good, essentially? So in order to give you an idea on what's going on, I'm going to recall what happens in the frequencies world. And in the frequencies world, if you are in these infinite dimensional models, what happens is that actually you cannot win on every side. What does it mean by that? Is that you have two sides of the story. One is the honesty, what they call honest confidence region, which is uniformly the coverage is 1 minus alpha. That's honesty. But you also want to have, because if you take the set to be the whole set, then on average, I mean, uniformly you're better than 1 minus alpha, but then you haven't said much, have you? And so the idea is to find a set that's small. And so you're going to be adaptive, optimal, if the radius of your ball is optimal in terms of that would be the minimax estimating rate in the functional space you're considering. Okay? Well, that's a bit technical, but essentially the radius is optimal over a collection of parameter classes. Huh? The problem is that what happens is that in these infinite dimensional objects, words, let's say, typically it's not possible. So you cannot be adaptive, optimal, and honest. So you have to lose something. So what do the Bayesian lose? Essentially, if you recall, the Bayesian, I'll go back here. No, there. Yes. The Bayesian, because they are going to be optimal, adaptive in terms of by hierarchical Bayesian modeling, you are easily optimal adaptive, and so you know that you're not going to be honest, because you cannot be both. And so how dishonest you are, is it important? And that's all of the kind of stories that you want to understand. And so to be able to understand that, you have to understand the subset of the parameter space for which you're going to be honest. And if this subset is interesting for you, then you don't care about being dishonest somehow. And so the idea, this has been going on in the frequencies literature, and recently there is this nice paper by Botton, Szabo, Harry van Santen, and Ad van der Waart, where they've been working on a specific model for which you have exact computations. So the model is a bit like of a toy example, essentially. So you imagine that you have an infinite sequence of observations around an infinite sequence of mean with a Gaussian noise with variance 1 over n. So it's called the white noise model. And that's a bit like a toy example. If things don't work well in the white noise model, they are going to work terribly in every kind of other models somehow. So if you put a Gaussian white noise model here, and then the Gaussian prior on the parameters, then you get a Gaussian posterior distribution. So you exactly know the shape of your parameter, of your distribution. And here you put a Gaussian prior on the parameters with a variance that goes to 0 at a certain rate. And so the rate depends on these hyperparameters. And typically, if you choose lambda to be either with a prior on lambda or to do what was said by Dino before using the maximum marginal likelihood estimator, in other words, you're finding lambda hat that maximizes the marginal likelihood integrating out the thetas here. Then you get an adaptive procedure because you don't have to fix lambda. You can learn it from the data. And what happens is that, so you've got this posterior distribution. Here it should be theta hat. You compute the posterior mean. And then you compute a credible ball around the posterior mean. And you inflate the radius of the ball. So you have this ball with radius q and alpha. The posterior mean, if ln was here, if ln were equal to 1, you would have the posterior probability of this set to be equal to 1 minus alpha. And so you inflate the radius to make sure that it's actually slightly bigger than what you would have, to make sure that the coverage is going to be correct. And so what they proved is that you have, by doing something like that, then you have the right radius asymptotically. So it's going to be adaptive. But that's not a big of a surprise. It corresponds to the usual literature. More interestingly, if you consider a certain subset of points, and I'm going to describe what they are, then the confidence region, the frequentist coverage of this set is going to be bounded by 1 minus alpha uniformly. So you're going to be honest, at least on this set. And so the question is, what is this set of good guys, the good points? The good points are what they call the Polish tail points, the theta that satisfies the Polish tail condition. And what the Polish tail conditions essentially tells you is that, so here, you're looking at what remains if you had truncated the series at n. So you have this series of thetas, you truncate the series at n, you look at the L2 norm, and that's the bias. So that's what remains if you truncate it at n. And what it says is that the bias must go down to 0 as n goes to infinity in a regular way. If you have these sort of long flat parts and then it goes down, and then a longer flat part and then it goes down, then it doesn't work. It collapses completely. So this Polish tail conditions essentially tells you that the bias in the L2 norm, by truncating the series, goes down regularly in n, as n goes to infinity. Just an illustration to show, so these plots come from their paper, to show that it's really important because you don't see it at all otherwise in the Bayesian world. So here, the black is the truth, the blue is the posterior mean, and you don't see it, but there is a shaded gray that corresponds to draws from the posterior. So you can look at them as credible bounds, essentially. And so, so here, n takes different values, and n is increasing as you go down the slide. And so what you see is that it's completely off. So essentially here, the bound is very narrow around the mean, and it's completely missing the true function. But here it's fine. So n has increased, and then you're capturing what you want. You're still capturing what you want, but not anymore. And so you see that as n increases, you are good, and then you're bad, and then you're good, and then you're bad. And so you're not going to be good at the end of the day. Not always, let's say. And whereas if you take a Polish tail function, which is the black one here, now as n increases, you're going to be better and better, and you're really going to capture, with your credible bounds, you're going to capture the true curve. Yes. So our aim was to sort of be able to elaborate from that and try to understand really what's going on and to get some tools to prove these results for general models. So just to, why is it not general? It's because, as I said, you have a Gaussian model with a Gaussian prior, so you have an explicit expression. And so what's going on is because it's Gaussian, the key things are bias and variance. And so what happens is that by looking at this maximum marginal likelihood estimator, you're going to find a trade-off between bias and variance. So it's going to concentrate on values that makes this trade-off, essentially. And by making this trade-off, then the bias is going to be of the same order of the variance, and so the credible bounds will be also confidence bounds. And that's ensured by the fact that you have this Polish tail condition on the truth. The question is, what happens if you're not Gaussian anymore? If the likelihood is not Gaussian, or the prior is not Gaussian, or both. And so that's what we've been studying with Botonde, which is a generalization of that. So in a certain framework. So what we've done is that you're considering a parameter space that can be written as a collection of finite dimensional parameter spaces. So we've written them as embedded. They can be slightly different than embedded, but morally you have to think about them as embedded. So it's a bit like you're looking at the expansion and you truncate it at k, and then you're having different k's, and so you're having all these possibilities. And so if you're fully Bayesian, typically what you do is you put a prior on k, and then given k, you put a prior on the parameter theta. But you can do the empirical based version of it, which is what we described before, where for each k, you have a prior on theta, and then you compute the marginal likelihood at k, and you take the k hat that maximizes this marginal likelihood. So if you do that, you do MMLE, and essentially, asymptotically, these two methods are going to be equivalent. So now we're still looking at credible bounds, but this time with a specific D that corresponds to the statistical problem we're considering, and centered at the MLE, at the posterior mean. Again, I'm inflated the radius. So if L equals 1 here, I have a credible region. But I'm inflated the radius to make sure that it's sort of slightly bigger than I would have if I were doing a purely Bayesian world. And so what I want is to find a subset of theta for which the coverage, the frequentist coverage, is going to be good. Because I know that very easily you can prove that with this kind of setup under sort of normal conditions, the coverage, the frequentist concentration rate is going to be adaptive, minimax, everything is fine. So you're going to be adaptive optimal, you're going to be dishonest because you cannot be both. And so the question is, I want to know at least a subset of points for which I'm not dishonest for these things. And somehow the theory is exactly the same as what happens in the Gaussian case, but nothing is explicit. So you have to understand these infinite dimensional integrals, and so you break down the puzzle somehow. And what happens is that, but it's the same story. So here you define a bias, but by looking at the distance of the true function to the model, so here if you're in model theta k, you're looking at the minimum distances between theta naught and theta, when theta is in theta k. That's called the bias. And what you're asking, so these sort of good guys, the good points for which you're going to have good coverage are points for which the bias, as k increases, the bias is going to go to 0 regularly. So you won't have these long flat parts and it go down, long flat parts and it go down. If you have something like that, then you'll be screwed up and it's not going to work. So really, this we call it, because we were completely lacking imagination, we call this generalized Polish-Tail condition, but it's a generalized version of what happens in L2. It's exactly the same story, essentially. And this is a key thing to understand what's going on. Because what happens is that under this generalized Polish-Tail condition, the posterior distribution on k is going to concentrate on the value of k for which you're going to have sort of the equivalence between trade-off between mean and variance. Bias and variance, sorry. But it's different because it's not Gaussian. So how does it work first? And then I'm going to explain the general ideas behind that. So if you have this GPT condition, so the bias is going to 0 regularly with k. And the usual type of conditions for posterior concentration, so here it's nothing exciting. And this kind of unpleasant conditions, actually, that essentially you can view them as saying that locally, the metric that you're considering in model theta k looks a bit like a Euclidean metric, essentially. So if you have this kind of behavior, so locally it's a bit like a Euclidean matrix, and you have the Polish-Tail condition and the usual story, then what happens is that if you blow up the credible bounds by a factor log n, you've got adaptation and the right size. So you're optimal in terms of size, but you're also honest in terms of coverage, at least on these points. So what does it mean? So how does it work? Just nothing technical, really. But the key thing to understand what's going to happen is to understand where the posterior is going to live for k. Is it going to live for values of k that are too small, too large, or not, essentially? And because if it lives on a value of k that's too small, then you will have a big bias compared to the variance, and the coverage is going to be terrible, essentially. And so what happens is that the equivalence of bias-variance trade-off becomes a trade-off between the bias and what I call prior complexity. And so essentially what happens is that the posterior distribution is going to live on values of k that makes a balance between the bias and the prior complexity. The model complexity, but the model complexity in terms of the prior. And so why this k log n term is you can look at it as a prior complexity? It's because essentially, if you're having something that looks like a Euclidean distance, locally at least, if you look at the log of the prior mass of neighborhoods of order k over n, then it's a bit like minus k log n. So this k log n is essentially comes from the prior mass of neighborhoods of the truth. And this is the key quantity to understand the behavior of the marginal likelihood, essentially. And so what happens is that with a generalized Polish-Tail condition, then the posterior distribution is going to concentrate on this set of points that such that you do have this bias between bias and the trade-off between bias and prior complexity or model complexity. And also, it also ensures that this set is not too large. So just what kind of distance can be considered in this, for these kind of things? It depends on the models, of course. And there will be distance. It's over. Yeah. There will be distance that are typically like statistical distance. So they cannot be too different from statistical distance. In the case of density estimation, that's the Hellinger, for instance, or L1. For the white noise, it's the L2, as we said before. For the regression, it would be the L2 on the empirical design. For the classification, it's going to be the Hellinger on the empirical design as well. And so you could go on like that. But there are going to be statistical distance, like natural distance in the statistical problem you're considering. And so what happens is that you can prove that with this kind of framework, you get adaptation. So the side is going to be correct. The coverage is going to be correct, so long as you consider only these Polish-Tail conditions, essentially. So the bias is going to be well behaved. So you can do it for density estimation with histograms, regression and classification as well, and you can prove all that. So just to conclude, so we have these new tools now to derive confidence on credible regions and statements on the size, but statements on the size are fairly straightforward. So really the difficult part is the confidence story. There is still a lot to do, because for the moment, the only models for which we have results are simple models, where the structure is not too complex, and simple priors as well. In other words, locally, you must be like a Euclidean model. If you have a distance that's very different, for instance, if you take a mixture model, then locally you're not anymore a Euclidean model, then you don't really know how to do it. It doesn't mean that it's not going to work, it's just we don't have the mathematical tools to answer these kind of questions. And also another thing that bothers me, maybe it doesn't bother you, but it does me, it's this fact that we have to blow up the factor, and actually it's quite important, I think, because it tells you what happens. You have to blow up the credible region with a factor log n. So obviously, we are not saying that if you don't, you're going to have bad coverage. But I do believe that you're going to have bad coverage if you don't. And the reason is because of this log n complexity that pops in. It's a bit the same as a BIC. Huh? In the BIC, you've got this log n, and the log n's come from the same story. It's exactly the same. Because of this log n complexity that pops in the story, the posterior distribution is going to concentrate on values of k that are too large, too small. Too small by a factor 1 over log n. And you have this bias, and so to get rid of the bias, you have to blow up by a log n term. And I think it's there. We haven't proved that it's there, so we don't have a lower bound, but I'm pretty convinced that it's there, essentially. So it's a bit embarrassing. That's the conclusion.